basically, how did this come about? Particularly over the last few years, I've been building UKMARS bots with Kes School in Stratford. And when I was chatting to their new IT lady about 8 months ago, she said, oh, well, we're doing Python now. So I thought, well, I'd better make a Python UKMARS bot, which I did initially. And then I was thinking about, well, what do we do next? So we said, well, it probably ought to be a maze solver rather than just a simple line follower. So over the last month or two, I've been just putting together a simple maze solver based upon a UKMARS bot Python implementation. Okay, so if I just go to there and click to there, right. Okay, so hardware-wise, what have we got? It's a standard version 1.3 main board. It's Adrian Edelston's PCB for the 4 wall sensors using visible light, 4-degree angle LEDs, nice and small beams, 2 pointing forwards at the sides and 2 angled ones, pretty standard stuff. The Python mods for the main PCB are the ones I've described previously. So you knock out the battery feed resistor, I think it's an R7, disabled the 5 volts from the CPU, join the 5 volts to the 3 volts and short out the 4-way switch and stick in a Cytron Maker Nano RP 2040 pin compatible CPU board instead of the Nano, and you have a Python-based UKMARS bot. The gears and the motors I'm using are slightly unusual. I spotted them about 2 months ago on Pi-Hut. There are 30-to-1 6-volt micrometal gear motors, but they come with the magnetic encoders and the magnets with the whole sensor thing, all there with a handy little plug that you just plug into the top, which we can then wire straight into the PCB. And they're £11 or thereabouts from Pi-Hut, but they've only got one left. But they actually get them from dfrobot.com, and they're about $11 plus whatever the shipping is from the States if you get them from DF Robot. I went for something with a slightly higher gear ratio because I thought that way I get more torque, and also I get less sort of overrun and control, because if I change the speed of the motors, it changes almost instantly. And it's standard battery I'm using, rechargeable LiPo, the lighter 1200 milliamp ones, which get for about 10, 15 quid, depending on where you get them. So, and again, there at the bottom, you can just see the picture of the motor with its nice little plug in the top, and you even get given the plugs with the different leads and everything. So quite a handy little way of doing everything without too much messing about with encoder, magnets and boards and things. Okay, software development. So software, I was using Thonny. I've been using Thonny for a while, so the version I've got is the 3.3.10 IDE for Windows 10, which is a 64-bit version, and I'm just running it on an Acer V15 Nitro laptop, which is what I'm presenting on now. And that includes the IDE that you just load up from Thonny.org, gives you MicroPython 3.7.9 and TK 8.6.9. I think, Peter, you were asking previously about whether TK was there, and it comes as part of the package. Later versions are available. I think the latest is 4.1.4, but don't use anything earlier than 3.3.10. Otherwise, you won't have support for the RP2040 chip. Okay. Once you've got the development environment loaded, you need to select the interpreter because it supports lots of different interpreters with different devices. So basically, you go to the run bit, and you click on that, and you then do select interpreter, and it comes up with a number of options, one of which is MicroPython, Raspberry Pi, Pico. So although we're not actually running on a Pico, we're running on the Citron maker. It's got the same RP2040 chip in it. So from that point of view, it thinks it's a Pico, and it works exactly as if it was a Pico. And in terms of the things you need to import at the beginning of the program, the pins, the ADC for the ADC converters, the PWM routines for driving the motors, and then because the board's got a couple of NeoPixels on it, 3-color LEDs, if you want to play with those, you stick the NeoPixel bit in, time as usual, and arrays, again, just for doing bits and pieces of having arrays in your software. I didn't take the approach of going back to the standard set of code that Peter and others have put up, because I wanted something that was a bit simpler and a bit quicker and easier for me to put together. So my simplified approach, there is no fixed systic in my system. There are various processing loops that run depending on what it's doing, and they just run as fast as the code wants them to go. And because I can change the speed, although I don't change it very often, quite rapidly because of the 31 gear ratio, I haven't actually bothered with any acceleration or deceleration profiles for the motors. Most of the time, the motors are just running at a standard fixed PWM value, and the only time that changes is basically when they're going around a corner, or if they're doing a little bit of wall avoidance, or doing a 180-degree turn. So again, I haven't had sort of the separate forward and rotational controllers that Pete would normally put in. The encoders are just used to measure the distance gone on each wheel. And the encoder interrupts are set by the following 4 statements. So basically just set those 4 things. And then as each of the interrupts occur, it either goes to the left count 1 routine or the left count 2 routine, or if it's the other wheel, it goes to the right count 1 or the right count 2 routine. And all those routines do is basically just add 1 to the relevant encoder count and return. What's interesting, and I don't know quite why this is, and I just haven't probably thought about it enough, is that of the 2 counts that you get from one wheel as it goes along, the first count is twice as high as the second one. So if I get 1,000 counts on left count 1, at the same time I'll get 500 counts on left count 2, and the same obviously for both motors. So it's something to do with the pulses coming back from this the encoders that I've got. As with all my other mice, I like to have lots of programs selectable, especially test programs, but because the 4-way switch isn't working on the Python, because I haven't got a spare analog input for it, I just use the buttons and the sensor LEDs to show me what the program number is, and then select it. And because I've still got the standard PCB button at the back, but I've got a separate button as well on the Citron Maker Nano board. So between the two, I can cycle through program numbers and then select one using one of them. Within each of the routines, I've got little debug mode statements. And basically it says if you're in debug mode, then every time you go and do anything, go and print out the key variables. And then at the end of each move, and I'll talk about what I mean by a move, actually pause for 2 seconds so that you can see what you're doing, what it's done, where you think it's gone, where you think it's gone wrong. Okay. Right, I'm just going to talk about some of the main routines, and we'll start with the maze solving routine and the main processing loop. Excuse me, I've got a bit of a cold, but we'll get through this. Right, so at the beginning, I set up the maze and the wall arrays, which is, pretty straightforward stuff. All the way around the outside, plus an extra one at the start cell. And I set up some initial values of variables, and I call a calibrate routine. What the calibrate routine does, it just looks out with the two side sensors, and it then measures the two side walls and just logs those, basically as saying, okay, that's about where I think the walls ought to be when we're going along. Okay. At the start, it waits for a button to be pressed to kick the thing off, and then it backs up to the rear wall, and it does that so it can get an accurate distance for the travel in the first cell. And then the main loop in the program is doing once round this loop at each cell boundary. So basically, each time we're going to go round the loop once, we will start off at a cell boundary. And at that cell boundary, we'll read the photo sensors, which will allow me to set the walls in the wall array for the cell that we're looking into, which will be, in effect, the one just above it. We'll then flood the maze in the maze array using the proc list array, which I'll talk a bit more about in a minute. And then we call a routine that says decide where you're going to go next. And that basically says either we're going to go one cell ahead, or we're going to turn right, or we're going to turn left, or we're going to turn around. And then we call the routine for whichever of those things the where do we want to go next routine has told us to do, which will take us to the next cell boundary. So if it's one cell ahead, it will move us forward 18 centimeters. If it's a right turn, it will go forwards a bit, do a turn, then forwards a bit more until it gets to the cell boundary again. And then also, when we get to the end of a cell boundary, we check to see if we've reached the target cell, if we're going out, or if we've reached the start cell, if we're coming back. And if the target's reached, we go to the center of the cell, stop the mouse beep, and then reset the route direction for the flood to say flood it back the other way. And then we go into the main loop again and run exactly the same thing in the opposite direction. And that'll take us back to the start. And when we get to the start again, it'll just basically turn it round again and set it off again. Okay. So the key bit in terms of deciding the route it takes is the where next routine. What it does basically, it looks in turn at each of the four adjacent cells to the current one, and determines if there's a wall between the current cell and that cell. If there's no wall in the way and the flood number for the cell it's looking at is lower than the flood number for the current cell, then that's the one that we want to go into. And then depending on which direction we're currently heading and on which side of the lower flood number is, we decide whether that means we're going ahead, turning right, turning left, or turning round. So pretty straightforward stuff. We pass the type of move back to the maze solve routine in the move field for it to call the relevant routine to then execute the move. If there are several possible moves, i.e. several of the adjacent cells without walls have the same flood number, same lower flood number, the sequence of the tests above will prioritize the one that goes straight ahead. And that's just simply the sequence in which the coding statements are in. And it just seems sensible that if you've got a choice of going straight ahead or turning, going straight ahead is simpler. Right, so wall following. This is something I learned from Peter, which is not to do wall following, but to do wall avoidance. So at the start of the run, calibrate routine measures the two side distances in the start cell. Okay, so that gives us calibration values. When we're moving ahead in the go ahead routine, which is a little routine that says just go ahead a specific distance with the encoders, it reads the current side distances with the photo read routine. And if either wall is nearer than the calibration values, it uses proportional control to adjust the motor speeds to move away from it. So I'm not trying to follow a wall and keep myself at a fixed distance from the wall. I'm simply looking at the two walls and saying, if I've got closer to the wall than my initial calibration value, I probably ought to move away a little bit. And if I'm only a little bit closer to it, then it'll only move it away a bit. And if I'm quite a lot closer to it, it'll move it away more. What this approach does, it avoids the mouse turning into the wall as the beam spot drops off the end of a wall, which was always a problem in the past when I was doing sort of wall following. And also, if there are no side walls at all, we can still get the mouse correction off the posts, because as you then go past the posts and it sees the posts, it will then see whether or not either of those posts on each side are closer than the initial calibration values. And if they are, it will then move it off. So even if you just got a row of posts, you can still get a reasonable rundown through that section of the maze. So turning left and turning right, pretty straightforward. We move forward about a centimetre from the cell boundary. And then we reset the inner wheel speed to a third of the outer one. And then we turn for the number of encoder pulses on the outer wheel that we want, which will basically make sure we get around the 90 degrees, whilst checking that the inner wheel encoder count times 3 equals the count from the outer wheel. And we use some proportional error to adjust the motor speeds to maintain the 3-to-1 ratio. And that loop just runs at full speed again. So again, there's no sort of sysdig saying, oh, you're doing this once every millisecond or whatever. It does that as often it feels like it can do it. Once we've done the 90-degree turn bit, we still won't be at the cell boundary. And so we reset the inner wheel back to the speed of the outer one. So basically it's back to our sort of standard base speed, and then move forward about a centimetre or whatever is required to bring us up to the next cell boundary. Whilst moving forwards at the start and the end of turn, wall avoidance will be active, because the routine that does the moving forwards straight will always be doing wall avoidance. So that helps to keep the mouse aligned at the end of the turn. Right, flood routine is obviously a straightforward flood routine. I'll run through it very quickly, but it's pretty much so you specify the start and the finish to the routine to say where you want to start it and where you want to finish it. It clears the flood table to all high values. Well, in fact, 283, I think, is the number I put in them. As long as it's more than 256, it'll do. We set the current cell to the start cell and put 0 in the start cell. And then the loop basically checks for walls in turn on each side of the current cell. If there's no wall, it puts a cell number +1 in the adjacent cell, unless that cell already has a lower number in it. For each flood cell that we update, we add that cell number to the proc list, which basically is just an array that's just keeping track of cells that we've looked at and that need processing. We then get the next cell number from the proc list and set it as the current cell. Carry on doing that, but the only thing we're going to do is just to check if the item just processed is the finished cell number, and if so, we go out of the main loop. If we run out of proc list items before reaching the finished cell, we mark it as a flood failure and pass that back to the main routine. It's only about 50 lines of code, so it's not a complex routine at all, and it seems to run pretty quickly. So I've talked about some of the key routines. There are actually about 40 routines in the system. They're pretty straightforward. Backup is going backwards up to a wall to get yourself aligned within a cell. Beep, pretty obvious. Button, wait for something to start. Calibrate, the initial calibration when you're setting off, just to do the two side walls. Check speed is just to make sure that when you adjust the motor speeds, you don't set them above 65,000 or below 0. Encoder reset just resets the encoders typically at a cell boundary. So rather than keeping an ongoing count for forever, we just reset the encoders when we're about to do something. That's just a test routine. That's a test routine. Flood clear, okay, is the initial thing that clears the floods. Flood maze we just talked about. Go ahead is the bit that says just go straight ahead, doing wall avoidance for the number of encoder pulses that have been asked to do. And again, it just sets both motors to the same standard base speed and just waits till the encoder count's been reached. Go one cell ahead is basically using the go ahead routine to move it forward 18 centimeters. Halt's pretty obvious. Lead test is obvious. These counts are the encoder count routines. Motor test, okay, yeah, another test routine. Now time is just if I want to actually see how much system time has passed, I can use now time routine to get in effect a millisecond or a microsecond count from the system. Pause, as I say, in debug mode, pause is simply used to stop everything for 2 seconds, and then it starts it off again. And that's really good for actually seeing what's happening while it's moving through the maze and while it's deciding which way to go and actually doing the turns and things. Photo read standard, reading the sensors, testing them. Prog disp, what that does is that just displays on a couple of LEDs the program number that we're about to select. Write count 1 and 2 are the encoder counts. Setting the outside walls is part of the initial setup of the maze. Set walls is the routine that gets called at the beginning of each cell. Once you've looked into the next cell and you see what walls are present in the cell when you're at the boundary. So it just gets called again at the beginning of the cell boundary. Show flood is a print routine that just shows me what the flood table looks like. Show LED walls is routine that says as you're going along, the 2 LEDs on my sensor board will tell me whether or not it thinks it's seeing a left wall or a right wall. Show walls is a print routine that prints out what it thinks the current state of all the walls are in the maze. Stop, pretty obvious. Switch read, pretty obvious. Switch test, pretty obvious. Turn around, turn left and turn right are just the routines that say, okay, go forwards, turn right, turn left, or if it's turn round, go forward to the center of the cell, do a 180 degree, then if there is a wall behind you, back up to that wall. And if there isn't a wall behind you, then don't try and back up to it. That's something that confused me for a little while. Well, I got that sorted. Warenext is the thing that says, okay, where should we be turning or going straight? And then Maysolve, it's the Maysolving routine. You got 3 arrays: the walls array, the maze array, and the proc list. And I say in debug mode, routines print out when called with key variables and false at the end of each move. There's about 1,000 lines of code in all in the 40 routines in the system. And it's taken me on and off probably about months, I suppose, to write it. I've had the odd bit of time here and there. So, at home I've got a little 6x3 maze, but just to make sure that it can do more than that, the maze that I'm testing it on is actually defined as a 6x4. So there's an imaginary extra row of 6 cells down the right-hand side, which just happen to be blocked off by a wall. Start cell bottom left as usual. Target cell in this case is 4 rows north and 3 to the east. So that's where we're aiming for. And this little routine is set up with this pattern so that there are 2 routes to and from the target cell, and it won't necessarily find the best one the first time. But we'll see what happens. So what we're expecting it to do, basically, as it goes forwards, it will go up to here. And then at this point, it would have liked to have turned right there, but it can't because there's a wall in the way. So it decides it may as well carry on. So it goes up to there, and then it manages to turn right, and then it has to come back to the target cell. Having got back to the target cell, it's now looking for a way back, and it should, from the flood routine, realize that there's a route down this way as well. So it'll go down this way, down to head 2 west, and then drop 1 south, and that should get back to the start cell. Subsequently, now it knows that this is the shortest route rather than this longer route around the top that it initially found. So it should head 1 north, turn right, head 2, and get to there. Okay. So does it do it? Let's have a look. Oops. Okay, so yes, it does what it should do. I obviously haven't tested it fully on all possible mazes, and I'm sure there's a bit of tweaking that can be done on some of the turns and also checking distances and stuff like that. But in terms of a basic bit of maze solving code, it sort of does the job. And certainly it's a good starting point for somebody who wants to have a play around with something like that, doing it with Python. If you go to my website and the UKMARS section of it, you'll see a number of bits and pieces. The stuff that I did on remote access from the phone, some stuff to do with the line following in Python, the Python mods that you need to do to the main board, and also this presentation. You'll find it up there. But in terms of what it does, and it does the job reasonably well from what I can see at the moment. that's what I've put together. So hope that is of interest. Have we got any questions?
Thank you, David. Thank you for that. I have a question here. I'll start the questions off and then please join in, everyone. Are there any features of Python that you've either found particularly helpful and beneficial for writing the maze solver, or any that you found more difficult than, say, some of the other languages you might have used in the past?
I don't think there's anything particular that makes it a lot easier than any other language. I mean, it appears superficially slightly simpler than sort of C or something like that. But at the end of the day, it's assignment statements, if statements, when statements and stuff like that. And they're all pretty similar. It's just the syntax is slightly different. The one thing that I do find annoying is the fact that the block structure is defined purely by indentation. So whereas within C you'd have a if something or other and then open a bracket and you put some statements in it and then it does everything till the closing bracket. With Python, you do your if statement and then you have to go to the next line and indent, and you've got to keep that exact same amount of indent going for all the things that you want to be done by that if statement, and then you have to outdent, basically back out to carry on. And if you're copying code, because I tend to not put Python up on the school website as a PY file because I don't think it lets them download any executables, then I tend to convert code to PDFs. And in that conversion, some of the tabs and spaces don't always come off exactly the way I was expecting them. And so you quite often end up, when they take the PDF code and put it back into Python, the indentation isn't always right. And that's a pain, just trying to sort that out. So I'd rather have a language that has a more better defined block structure than simply indentation. But apart from that, I don't think there's anything particular in the language that is better than any of the other 25 languages that I've learned over the last 50 years.
All right. Okay, thanks, David. Anyone else got questions for David? I can't see any hands up.
I actually would have one question.
Yeah.
Actually, I'm right now also building Micromouse, and I have these time of flight sensors to measure the distance to the walls. Basically, I went through this UKMARS bot guide on the website, and basically what you are doing is I understand you basically have your own sensors, that you have this LED and then you have this Bluetooth transistor. And from my understanding, the benefit of your sensor is that you have much higher sample rates, that you basically can have a very high sample rate. And these TOF sensor that I'm using, I think it has a sample rate of up to 50 measurements per second, maybe 20 measurements per second under bad light conditions. Right. Is this actually an issue? Is it still possible to use it, at least in this slow measuring run, or wouldn't that be enough?
It depends a little bit how fast you're traveling. I mean, with the scheme that the standard Micromouse uses, then typically we're reading the side sensors 1,000 times a second, or Peter reads them 2,000 times a second, I believe, when he's sort of going at speed. So there's quite a difference, obviously, between 50 times a second to 20 milliseconds. So we can typically easily read them 20 or even 50 times faster than you can, which simply means that if you're traveling quite a bit of distance in that time, then you can be a bit further out before you realize that you've missed it. But also, if you're just measuring off the posts as well as you go past, again, depending on how fast you're going, if you're only doing did you say 50 readings a second, you could go past a post before you've seen it between the readings, or you just catch the edge of a post rather than sort of seeing the whole of the post as you go past.
Yeah. Basically, I mean, as I understand, it's like people always do this one scanning run where they just scan the entire maze, and then in the second iteration, they just do the path one where they then just only go the path is tracked from the starting cell to the final cell. And I mean, from my understanding, wouldn't it be like completely enough to only use the photo sensors only in this scan iteration, but not in the follow-up iterations? Or is your impression on these? I mean, I use this Lulu encoders, aren't they just not precise enough to do like the path one completely without the photo sensor?
I mean, once you found the route to the maze, then obviously, in theory, you can do it all on the encoders. But it's nice to be able to just check the walls, because you never know if you're going to get a bit of slip on the corners or a bit on the acceleration or deceleration or run over or something like that. But you can definitely build a maze solver using the technique that you're using.
And that's like how most people are doing it. That also in these fast ones, people usually use their photo sensors to measure it, or is it also that there are many approaches of people who do the fast one only with the motor encoders?
I would guess, and I think Peter will agree with me, probably 90% at least use the beam and the photo sensor, just measuring the amount of reflection you get. A lot of people just use infrared so as to avoid issues with ambient light. But again, with schools, it's better to use actual light that you can see. And to be honest, it's plenty good enough for the sort of speeds that we run at anyway. Yes, you can do. We've seen people who send a beam to the side and measure the angle that it comes back at. I've done it in the past with ultrasonics. I've tried it with single line cameras, a whole load of things. And it took me a while before I realized that what everybody else was doing was actually much better than what I was trying to do.
Yeah, we've got a hand up from Andy. I've got a hand up from Andrew. Andrew, have you got a question? No?
Andrea's microphone's off.
Yes, sorry, can you hear me?
Right.
Andrea.
Yes. Andrea.
Can you hear me?
Yes, can hear you now. Do you have a question?
Yes, I had a question. I think David mentioned that he is not using Interact, so I was wondering if he has any information about what sort of speed the routines can run.
It doesn't affect the speed, whether you.
No, I mean not the speed of the Micromouse. I mean the frequency of updates for the routines. Like how often do you read the sensors? How often do you read the encoders and so on? Right.
Okay. Normally, most people will use a fixed time period, and they'll base it on something like a 1 millisecond sys-tick. So every thousandth of a second or every millisecond, they will read all the sensors, and they will read the encoders, and from that one they'll work out where they are and what they think they're doing. It doesn't really make much difference whether you're doing it with visible light or infrared. The only thing with visible light is if you want to be more away from, less affected by ambient light, you typically need to read the distance with the LEDs off, then switch the LEDs on and then read it again, and you take one from the other. And that gives you that. So in theory, you would need twice as many reads if you're using visible light. But even having said that, there's no problem in doing the reading of 4 sensors twice within a millisecond.
When using infrared, we would still do exactly that. No difference at all. We'd read them twice and take away the two to take the ambient light out.
There's something in your description, David. You said that your steering and other things use proportional control, and because of that, the frequency with which you do the updates is not really important. In that it doesn't affect the dynamics so much. If you had a PD controller or a PID controller, then the loop rates, the loop update rate, need to be taken into account. But if it's just proportional, it's much less important how frequently you read them. So in Python, if you don't have access to good timing, just read everything as fast as you can and get on with it, really, and that seems to work perfectly well.
Yeah, that's pretty much the approach that I took, because I wasn't sure whether Python would go off and do things, when I wasn't expecting them to, or you've got the now function, which does allow you to get the system timer, and you can then just work out how long has elapsed. So if you wanted to put in a fixed timing loop, you can do it with Python. But I just thought, well, let me just keep this as simple as I can. And if all I'm using is basically the encoders to say, have I gone far enough? Then I'll just read and sense and adjust as fast as I can within the time between. And then it's irrelevant whether Python goes off and does something for a millisecond here or a couple of milliseconds there.
It's also perfectly acceptable to run a full PD or PID controller if you just tell it the time interval. And so, again, we run on a fixed. We normally run on a fixed time interval because the resources are there. There's a timer to do that and generate interrupts, and it's kind of lazy, right? You know how often things are going to happen. But if you can do it quite easily running free, and if it takes a little bit longer on one loop and a little bit less time on the next one, as long as you know how long and feed that into the calculations, it'll work perfectly well.
Yeah, absolutely. And if you wanted to put that, more refinement into this, then no problem at all with doing that. Say it was more of a question of I had 3 or 4 weeks to sort of put this together, and was doing quite a few other things at the same time. As well as cracking a rib. So,
yeah, it sounds good. Sounds useful just to get something going that we could build from. You're right about the loop interval. If you look at something like Pick One or Pick One Turbo, that we had the video for its 15th birthday, that runs like that. It has no fixed loop. It runs the loop whenever it can, and fixes the time between the two. So that's fine. Do you run the motors directly off the battery or from the?
I run them directly off the battery.
Right. So you might that was always when you're not using a fixed period. It's a very good idea to make sure that the voltage is the same and doesn't keep changing. Otherwise, it changes your corners, and so as the battery goes down, you suddenly find that you can't get round as accurately.
Right.
It might be better to run it off a regulator.
My thinking was, given that the corners and the steering is controlled precisely by the encoder count and nothing else.
Yeah. But it's not that bit, it's the acceleration, because when you're going straight to go into a corner, you have to accelerate up the wheel can't instantly be at the high speed. And it's that bit that varies a lot, because as the battery voltage goes down, it accelerates more slowly, and that mucks up the whole thing. But maybe I'm going to have a closer look at your encoder thing, because that's interesting. You're checking the other wheel, so it's proportional to the first bit.
Yeah. Yes. So as I say, so if it takes a bit longer to do it, and again, because we're not running at really high speeds, and I'm not changing the motor speeds by that much, I'm assuming in effect that it instantly changes the speed on the inner wheel, which I know it doesn't.
Yeah.
But then the control between the two encoder counts, in theory, should sort that out.
Yeah, no, it's an interesting way. Again, Pick One does a similar thing to you, but it actually stops the inside wheel. So when it goes around the corner, it just turns it off and says, and then uses exactly the same high gear ratio thing and assumes that it just instantly stops, which of course it doesn't.
Yeah, now I was originally doing that, and then I found that getting the motor up to speed from stop was much more variable.
Yes, that doesn't surprise me.
So just dropping it down to a third of the speed and then pushing it back up to speed from a third seemed to be much more consistent.
Yeah,
because you haven't got this sort of starting torque sort of type thing on the motors.
Yeah, no, so that's why that's interesting. It was just looking at it actually going around the maze and trying to see the things it was getting wrong, and then it just seemed to be, it was okay because once it got round the corner, it was able to recover from that. The problems you get on a full maze, where you get ones where you could turn and you can't recover, and you've got to do another turn and another turn and another turn, and that's where the errors build up, and you really you lose from that. But I think there's an awful lot you can do to that. As you say, you're not looking for the edge of the post where you could correct the lengths and all that sort of stuff, which is all perfectly doable, I think, in there.
Yeah.
So I think it's a good start, and
well, that was the idea, to just put something up there that if somebody wanted a starter set, something that they can kick off with, and then seeing what they can do to sort out the sort of issues, as they say, when you go around the corner and then you've got 3 cells without any walls on either side, and you've got to do another left and a right. But
the other thing was, you said that you set it to a slightly bigger maze than you actually had, the solving routine. Is it still, I'm assuming it is, but is it still fast enough if you set it to the full 16 by 16?
I believe so, but that's something I need to do some checks on, and actually look and see how long it takes to do the full flood of a 256 cell. But it's a pretty fast processor on the RP2040, so I'm thinking it's not going to be an issue, but it is something I would like to do a bit of timing on, and I'll probably get back to you and let you know about that.
So there's nothing to stop you, David, setting that size up anyway, is there? I mean, if it's all blocked off, it'll never go there, but it doesn't know those cells are blocked off until it tries.
Yeah. There's absolutely nothing stopping me just changing 3 values in the variables at the start of the program, and then just putting in some now statements in to pull out the timings at the beginning and the end of the plug routine.
Sure.
I should be able to do that.
You can always do Derek's other trick, of course, which is not to do it the way that I usually suggest, which is as you cross the cell border, but after you've crossed the cell border and whilst you're executing the next move, unless you have to, keep going, turning around the loop. If you can start a solve, then you've got loads of time to do it. And there are 2 processors on there. You could use one of them. But that's overcomplicating things. I think it's an excellent job and an excellent proof of concept.
Yeah, I mean, part of the thinking is to go forward 1 centimeter before you do the turn, was partly because, that would be the time when you'd be doing the flood. And so if you did take a bit of time out there, then it wouldn't be a problem, because when you finish doing the flood, the encoders will tell you how far you've gone up to your centimeter. And as long as you haven't gone past your centimeter by then, you still got, you're in a position to do the turn.
It gives you a chance to do your wall avoidance as well while you're doing that, doesn't it?
Yeah.
Yeah.
You mentioned one of the encoder channels giving you double counts. That's on UKMARS bot. That's by design. Sorry.
That's all right.
It's because the two encoder channels are exclusive ORed to give you for reasons, right?
Yeah.
And that's so.
Yeah.
It's gone now, right? So your A and B channels coming off the encoders are exclusive ORed, and what you see is the A dash, which I can't do behind here, that one, and that one. Those are the two that you get coming in.
That explains a few things. I've been seeing very odd effects.
Yeah.
So if you look at these, if I can keep that's it. If you look at these, you're reading that one and that one.
Yeah.
And if you exclusive OR that and that, you get the A channel back, or you get the B. No, whichever one it is you get, right? You mess with it.
Yeah.
Look at the code. But if you exclusive all the two channels together, you'll get the proper clocking sequence back.
Yeah. So, but as far as I'm concerned, I simply just add the two together.
It's
and that tells me with my gearing, it's about 4,000 pulses that I get on a motor to do my one cell from 18 centimeters. So yeah,
this is true, but you don't get direction. So,
no, but hopefully, I'm only
hopefully you know which way you're going.
I know which way I'm going, unless I'm backing up to a wall, which is the only time I'm doing going in reverse. And from that point of view, I'm going to do it until I hit the wall, and then
a bit further,
and a bit further, basically. So I don't have a problem with that.
Right. Any more questions for David? No, well, David, thanks very much for soldiering through with the cold as well. And thanks for that great presentation. I'm guessing that if people are interested, they're going to go and visit your website now and pinch your code. And,
yeah, absolutely.
Yeah,
take anything you like off there. No problem at all.
Been there, done that already.
Oh dear. Okay.
I do have one suggestion for people who are struggling with the indents on their Python. If your editor or IDE has an option to use spaces instead of tabs, for the love of your sanity, turn it on. Never use tabs, because they will be interpreted differently on different systems. And then your layout and your PDFs and all that will come right.
Oh, that's a good point. Thank you for that.
Right. Excellent. Okay, David, thanks very much for that. Great. Thanks for doing it. Always great to have a topic. I know it's a load of work for people, and sounds to me like you're a little bit in the wars as well.